Welcome back. In this section, we'll be looking at the double angle identities for sine, cosine, and tangent. These double angle identities could really be thought of as a special case of the angle sum identities. For example, this formula for sine 2 theta, we could really think of this coming from the formula for sine of one angle plus another, because sine 2 theta really is the same thing as sine of theta plus theta. And then using our angle sum formula, we know sine of theta plus theta, that's sine of the first angle, cosine of the second, plus cosine of the first angle, sine of the second. And you can see you've got two things that are the same, sine times cos, so we have 2 times sine theta times cosine theta. Now, we can use this identity to help us solve an equation like this. We're looking to solve sine of 2 theta equals to cosine theta over the interval from 0 to 2 pi. Now, if I were to rewrite this as 2 sine theta cos theta equals to cosine theta, then I've got an idea of how I might solve this. I can see that if I were to bring the cosine theta to the other side, that I'd be able to factor out cosine theta. And so I would have cosine theta times 2 sine theta minus 1 equals to 0. And so that means I would have two equations that I would need to solve. I would need to now solve cosine theta equals to 0 and 2 sine theta minus 1 equals to 0, which is the same thing as looking to solve sine theta equals to a half. So now we just have two equations to solve. Cosine theta equals 0 and sine theta equals a half. For cosine theta equals 0, that one we can solve if we're thinking about the graph of the cosine function. There's two places where the cosine function is equal to 0. One of them is at pi over 2, and the other is at 3 pi over 2. Those are the two places where cosine is 0 in that interval from 0 to 2 pi. So we have two solutions already. We know that cosine of theta will be 0 when theta is pi over 2 and also at 3 pi over 2. And now we just need to deal with the second equation, which is where is sine of theta equal to a half. Of course, that's the same thing as looking to find out where is theta equal to sine inverse of a half. And if you're thinking about your special triangle, the 30, 60, 90 triangle, we know that there's one place that sine inverse would be equal to a half, and that would be at pi over 6. But of course, remember that there's not just the one answer that sine inverse gives you, there's going to be another one as well. Because if sine is equal to a half at pi over 6, there's another quadrant where sine is also positive and would also be equal to a half, and that would be in quadrant 2, with the same reference angle of pi over 6. So the other place where sine is equal to a half is actually going to be at 5 pi over 6. So it looks like we've now got two more solutions. There's the pi over 6 that we have, and also 5 pi over 6. So that means we've got four solutions in total: pi over 2, 3 pi over 2, pi over 6, and 5 pi over 6. We've also got double angle identities for cosine. Unlike the sine function where there was only one, there's three different versions of the double angle identities for cosine. The first one comes directly from the angle sum formula for cosine. If you're looking for cosine of 2 theta, that's the same thing as cosine of theta plus theta, which is cosine of the first angle, cosine of the second angle, minus sine of the first angle times sine of the second angle, which gives us cosine squared minus sine squared. So there we go. That's our first identity. The other two come from Pythagorean identities getting added into the mix. Remember that we know sine squared plus cosine squared is equal to 1. And so that means you could rewrite this either as sine squared is equal to 1 minus cosine squared, or you could rewrite this as cosine squared equals 1 minus sine squared, just by moving the sine squared or the cosine squared to the other side. And that's how we're going to generate the other two versions of this identity. So if we were to take the equation that we just had, that cosine of 2 theta is equal to cosine squared theta minus sine squared theta, and if we were to replace sine squared with 1 minus cosine squared, so using that Pythagorean identity, you get 2 times cosine squared theta minus 1. That's where the second of the three identities comes from. And for the third of the three double angle identities for cosine, that comes from taking again our cosine of 2 theta being cosine squared theta minus sine squared theta. And this time, instead of replacing the sine squared theta, we'll replace the cosine squared theta. So replacing cosine squared theta with 1 minus sine squared theta. And that's where we'll get our third identity, that it's equal to 1 minus 2 times sine squared theta. Okay, so now let's use this. We're looking at an angle in quadrant 1, and we know the value for tangent theta as 5/12, and I'd like to find the value of cosine of 2 theta. So if we're thinking about this, no matter which of the identities that I use, cosine of 2 theta, I'll either have cosine squareds and sine squareds, or just cosine squareds, or just sine squareds. But at any rate, I'm going to need to know the values of sine and cosine of theta. So that's going to be my first move here. I know the value for tangent theta, and I'm going to use that to find the value of cosine and sine. So we've got an angle in quadrant 1. There we go, nicely drawn. And we know that there's going to be a point on that terminal side. If we're remembering that tangent is defined as y over x, then that means we could take the y coordinate as being 5 and the x coordinate as being 12. And then we can find out what r is just using our formula that r is the square root of x squared plus y squared. Putting in what we have for x and putting what we have in for y, we'll find that r is 13. And so we can say, great, good for us. That means that cosine of theta, that's x over r, that's 12/13. And sine theta, that's y over r, that's 5/13. And now that we know the value for cosine of theta and sine theta, we can use that to find the value of cosine 2 theta. Because cosine 2 theta, that is cosine squared minus sine squared, or 12/13 squared minus 5/13 squared. And then the only thing left for me to do is just evaluate. So I'm just calculating that 12/13 squared, that's 144 over 169. 5/13 squared, that's 25 over 169. And then when I subtract, I get 119 over 169. We can also use these double angle identities to establish other identities. So for example, here we've got this identity that we'd like to establish, and I'm looking at the left side of the equation. It's got a couple of double angles in it, sine 2 theta and cosine 2 theta. So that at least gives me somewhere to start. So I will start with the left side here. Sine 2 theta over 1 plus cos 2 theta. And for the numerator, at least, I know what I'm going to do there. The numerator, sine 2 theta, we only had one version for that formula. That was just 2 sine theta cos theta. So that's what I'll put in for my numerator. Now for the denominator, this is something where I'm going to need to think strategically, because if you're thinking about the denominator, that cosine 2 theta, there's a bunch of different things that I could put in for it. I could be using any of these three identities that I had for cosine 2 theta. But I'm thinking ahead about eventually I want to have what I've got on the left side equal to tangent of theta. And you'll notice there's no stray ones lying around there, which means that I ideally need to get rid of this one. So I'm looking at the three identities, and I see that if I were to use the second of them, if I were to replace cosine 2 theta with 2 cosine squared theta minus 1, that the 1 and the minus 1 would cancel each other out, and so I would be in a much nicer position now. And at this point, we can see that there's some things that are going to cancel just nicely. The 2 and the 2 for sure will cancel, and there's a cosine theta that you can cancel from the numerator and also the denominator. And that gives me just sine theta over cosine theta, which of course that's the same thing as tangent of theta, which is the right side of our equation. So left side and right side are equal to each other, and there we go. We've established that identity. For tangent, the double angle identity, again, that's coming straight from the angle sum identity. So 2 theta for tangent, that would be the same thing as tangent of theta plus theta, which is the same thing as tangent of the first angle plus tangent of the second angle over 1 minus tangent of the first angle times tangent of the second angle. And since these angles are the same, then in the numerator you've got 2 tangent of theta, and in the bottom you've got 1 minus tangent squared theta. And now I'm going to solve this equation, tangent 2 theta equals cotangent theta. First starting off just by rewriting this with my tangent 2 theta identity. And while I'm here, I'm actually going to bring that cotangent theta to the other side of the equation. So we have 2 tangent theta over 1 minus tangent squared theta minus cotangent theta equal to 0. Now, I might be thinking about the fact that the first term is all with tangents and the second term has a cotangent, so it might make sense to take that cotangent and rewrite it as 1 over tangent. Now there's one move that you might be thinking of doing, which is kind of a problem here. You might be thinking about perhaps clearing out those denominators, multiplying both sides of the equation by tangent theta and 1 minus tangent squared theta so that you don't have any denominators anymore. But remember that if you do that, you are potentially losing solutions. You might be losing a solution for any value of theta that made the denominator 0. So to guard against that, losing solutions, what we're going to do instead is combine these two fractions together into one. I'm going to make one big fraction with a common denominator of 1 minus tangent squared theta times tangent theta. So that first fraction, top and bottom, I multiply that by tangent theta, giving me 2 tangent squared theta. And for the second fraction, I multiplied it, top and bottom, by 1 minus tangent squared theta. And so now I'll have 3 tangent squared theta minus 1 over 1 minus tangent squared theta times tangent theta equal to 0. Now there is a little subtlety here. You know that when fractions are equal to 0, that's where the numerator is equal to 0. However, don't forget that our equations that involve trig functions can be rewritten in a bunch of different ways. Namely, that tangent that's in the denominator, you could bring that up and make it a cotangent in the numerator. So actually, we could rewrite this as 3 tangent squared theta minus 1 times cotangent theta all over 1 minus tangent squared theta is equal to 0. And so now we know that, again, our fraction will be equal to 0 when the numerator is equal to 0. So in other words, we know that 3 tangent squared theta minus 1 times cotangent theta should be equal to 0, which leaves us in two different directions. One of them being that 3 tangent squared theta minus 1 is equal to 0, which we find out that that happens when tangent squared theta is a third, or that tangent, rather, is plus or minus the root of a third. The other track here that we'll be following will be where cotangent of theta is equal to 0. So we've got two little equations now to solve. One of them, where is tangent theta equal to plus or minus root of a third, and the other one, where is cotangent equal to 0. For cotangent, that one's the more straightforward one. If you're thinking in terms of the unit circle, remember that cotangent was defined as being x over y. And there's two angles where x over y would be 0. One would be if we're thinking about pi over 2. On the unit circle, that would be the point 0, 1. And that would give you a value for cotangent 0 over 1, which is 0. The other would be 3 pi over 2, the point 0, negative 1. That also would give you a value of cotangent for 0. So there's two values where cotangent is 0, one of them at pi over 2, the other one at 3 pi over 2. Now for the other equation, we're looking for where is tangent of theta equal to plus or minus the root of a third. Or in other words, where is tangent of theta equal to positive root of a third, and where is it equal to negative root of a third? Now the one thing that we know, of course, is since these two numbers are opposites of each other, then whatever the angle is that makes it positive root of a third and whatever the angle is that makes it negative root of a third, those would both have the same reference angle. So once I find the reference angle that gives me tangent of theta is positive root of a third, I can also use that to find where tangent of theta is negative root of a third. So let's look at both of these one at a time. Where is tangent of theta equal to positive root of a third? Well, if you're remembering from your special triangle that tangent being root of a third, that happens at pi over 6. That's one of the places where tangent has a value of 1 over root of 3. We also know that there's two quadrants where tangent is positive. There's quadrant 1, that was our pi over 6 that we just found, but there'll also be an answer in quadrant 3, where tangent would also be positive. Same reference angle of pi over 6, which means we're talking about the angle 7 pi over 6. So two places where tangent is 1 over root 3, that's pi over 6 and also 7 pi over 6. And now finally, to finish off, looking at where is tangent equal to negative 1 over root 3, there is going to be two quadrants where that's the case. There's quadrant 2, where tangent is negative. And there, the reference angle is pi over 6, which means the angle itself is 5 pi over 6. And the other place where tangent is negative is quadrant 4. And in quadrant 4, with a reference angle of pi over 6, the angle must be 11 pi over 6. So we have, for tangent of theta being negative 1 over root 3, that there's going to be two values that we find. There's 5 pi over 6 and 11 pi over 6. And so therefore we've got ourselves 6 different solutions. There's pi over 2, 3 pi over 2, pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. And then finally, just finishing off with these last two formulas. These two are really more used in calculus. There's a couple of places in calculus where things will be easier for you if you don't have any powers. And so we have a power reducing formula so that if you have a sine squared, you could replace it with something where there's no squared happening. Or if you had a cosine squared, you could rewrite it so that there are no squareds anymore. This is something, like I said, that's more important in calculus once you get there. That is something that you will need to do in a couple of places. For now, all we're really interested in is just figuring out where these formulas come from. And where they come from, not a surprise, is our double angle formula for cosine. Remember that cosine 2 theta, there's a couple of different ways that you could write it. There was, of course, cosine squared theta minus sine squared theta. There was also 2 cosine squared theta minus 1, which, if you were to rewrite that, just basically solving for cosine squared, that would be how we would generate the identity that cosine squared theta is 1 plus cos 2 theta over 2. You also know that cosine 2 theta is 1 minus 2 sine squared theta, and that, if you were to rewrite it, you could see that sine squared theta could be rewritten as 1 minus cos 2 theta over 2. And so there we go. Those are our power reducing formulas, which basically it's our double angle formula for cosine just rewritten.